Oh, good. Well, I started 5 minutes early and started a video as indicated by the chat, and nothing was streaming. It wasn't the encoder I use so you can see everything, and YouTube were not syncing up with each other. So I think I fixed it, but hopefully we don't see any more problems. If so, I apologize. Anyway, I'm here, so feel free to ask me questions. I'm happy to answer them to the best of my abilities. Shrink that window a little bit because it's kind of giant. I'm struggle busing it today, guys. I'm sorry. Hi, Haley. I'm glad I'm not the only one. Move these things around. I had it all set up and perfect and then had to restart everything because it wasn't working right. I hate it when that happens. We're on our last exam, everyone. Or Haley, at least. I don't know who else here. There are 4 of you, according to YouTube. It doesn't tell me who you are, it just tells me how many people are watching, so feel free to ask anything, though. I was going to do a quick, because I normally go over exams through email, and I just really don't have the time to do that tonight. I'm sorry. Not if I want to put together a decent exam for my biochemistry class. But I was going to... Oh, Kenny, I'm sorry. Yeah, I was going to show you guys the exam, basically the old exam, or practice exam as a lot of you guys like to call it. So that way you at least have something tangible to look at if you had questions on those. Haley, when you use platinum 4 oxide for the alkyne reaction, do you still have to specify that you use acetic acid? If you do, I don't count off, but I don't think your book usually shows that for whatever reason, so I haven't done it. You can't see the one for the exam for tomorrow? No, you can't see the exam for tomorrow. I haven't written it yet. That's what I have to do tonight still. I have a couple students who are like, I need prior credit evals for the military, and I need letters of recommendation for medical school, and I had 45 emails since I got home. And it's okay. We'll get through it. We'll get through it. Last exam, guys. We can do this. So anyway, this is the first question. And if you guys have other questions, like Haley just had, pop them up. But otherwise, I'm just going to go through this right now. So if you have... Which screen do I need open? Here we go. So this is just a labeling the functional groups kind of thing. And so we did learn a couple new functional groups on this exam that we haven't really seen before, even though we haven't really learned how to name them, but we do know what they're called. So this one here is a proxy acid. which would be that guy there. This one here, let's go ahead and circle all the different ones. There we go. This one up here would be a ketone. Down here, an epoxide. Remember, epoxide looks like a cyclopropane, but it doesn't act like a cyclopropane. I've got an alkene over here in the corner. And then I don't think that we've really seen this one too much, but it's just an ether. So if you were like, I don't think we've seen that one, I don't know if we've actually done that one in our class this semester yet. Other maybe than just in passing. I don't think I ever really spent much time putting it on the board. I honestly don't remember. So hopefully that makes sense. Well, calling the peroxy acid a peroxyl group would be incorrect. You know, Martha, I don't know. I've never heard anybody call it that before. Let me Google it. Oh, the peroxyl would be where it is deprotonated, I think. Have you seen that somewhere specifically? Oh, and that's talking about just regular peroxides too, not peroxy acids. So yeah, just call it a peroxy acid. It looks like the peroxyl is what you get when you're doing the hydroboration with the deprotonated peroxide. Yeah, peracid is another word for it, Rachel. G down. Okay. Make sure that shows up okay. Good. I'm on it, Haley. I'm trying. I didn't get there yet. I'm assuming this is the one that you're talking about, the nomenclature part. So, pull that up. Okay, so this one here, I've got a few components. So, looks like I've got a cyclopentane as my parent chain, right? And I covered priority groups with my class last year. That's why these aren't really a practice exam. They're more just like an old exam because they're not necessarily representative of everything we cover, but I like to give them to you anyway, just in case you think they're useful. What I can tell you is that the ketone gets carbon number 1, and that's for a reason that I didn't talk to you guys about. So if you're wondering why I'm assigning that carbon number 1, my answer is wait until organic chemistry 2, and I will tell you. So, I'm just going to say cyclopentanone and then 2-bromo. If you wrote cyclopentan-1-one, I wouldn't count that off. It's technically redundant because of the cyclic system and it being inherently carbon number 1. But if you named it that, I'd give you full credit. The second one down here has the same situation where it's kind of like, well, how do you know? Because it would be carbons 1 and 3. Hopefully you remember all the times where I've told you that a carboxylic acid is always carbon 1. But that's also those priority rules. So this here is carbon 1. And then this one down here would be carbon 3. So this is one we would not have learned how to name, but just in case you're curious, we would have 3-hydroxy, because when an alcohol does not have priority, it gets called a hydroxy. propanoic acid. So yeah, the nomenclature on this one isn't quite as relevant to what we've been doing, just because I got through a little more of it last year than I did with you guys. And with them, I didn't cover as much multi-step synthesis as I did with you guys. So like, that's the difference. 2,3-dimethyl-pentan 2-amine. So let me break out a little pin here. So that's pentane. I need a 2-amine. Wow, that is not looking good at all. I'm sorry, that's so ugly. And then 2,3-dimethyl. There we go. And then 3s-3,4-diiodo-butanal. So butanal would look like that. 3,4-diiodo look like that. And we're looking for S stereochemistry, which means we want our groups to go that way. I already kind of have it drawn in that format, so I'm going to make that bold, dashed line, hydrogen. So would not the methyl and the amine group be on the same carbon? They would be. I just didn't count it right. Thank you, Olive. Let me try this one again. If I can actually count 2,3-dimethyl, make it actually a little prettier than it looked before. If you look at that one, there's only one chiral carbon on that molecule. It's that one right there. So it could have stereochemistry, but okay. So hopefully those make sense. And again, if you guys have specific questions on anything, feel free to ask. I'm just kind of going through these. The number of the functional groups from lowest priority to highest priority, that's again with that naming. We have not done that yet. So just getting down to the section on reactions, where we're just all right. So just a bunch of reactions in this on this page, which is pretty typical. You'll see another one like it tomorrow. So in this case, I can predict some of the stereochemistry on some of these. I think I usually use the brush. Okay, so here we go. And the osmium tetroxide with the, oh, that needed to have a sodium with it. Look at that, Dr. Man. You totally left that off last year. Nobody said a word. So this is a dihydroxylation, and it adds in syn to each other rather than anti. There we go. And you'd actually get the same exact thing for the second one down, so I'll just say ditto. Same thing. If we're trying to do a reaction here where we're adding in a hydroxyl group and a bromine, that means we're having to do one of those halohydrin reactions, and we learned a couple ways of doing that. We can use some water and either Br2 or NBS, so N-bromosuccinimide, and we would want to use some DMSO as a solvent to dissolve everything. Okay. And then at the very bottom of this page, I have an alkyne being converted to an alkene, where the hydrogens were added on in a anti-format, so to give an alkene. So I have to use a poisoned catalyst. Lindlar's catalyst adds sin. So in this case, I need to use ammonia and lithium, and that'll get the job done into that stereochemistry. If you put on Lindlar's catalyst and hydrogen gas, I would give you partial credit for that, but you'd get a point off because you didn't pick one that would give you that stereochemistry that was shown. So let me scroll back to my... So I'll just stop right now and see if there are any questions or comments or anything like that. I think I've mentioned this before, but in case any of you've not, you don't actually use the H2 gas with lithium and ammonia. You don't need any H2 gas with it. The hydrogens come from the ammonia. Hydrogenation only brings it to a single bond, or could use a small portion of the required reagents to reach the same result. Kenny, that's the one that I've talked about a few times in class where you can't really control stoichiometric ratios of a gas bubbling through a reaction. So if you want to go from an alkyne to an alkene, you have to use a poisoned catalyst. If you want to do an alkyne to an alkane, you just do a regular one. So that one is in theory fine, but logistically you can't do it. So that's why we have these poison catalysts. Good questions, good questions. And I think, Rachel, you had asked that, I think, in email as well. So that, okay. This reaction that I have up right now at the top, going from an alkyne to a carboxylic acid and carbon dioxide, we've only learned one way that we get carbon dioxide out as a product on anything, right? And that is to use KMNO4 and acid on an alkene. Okay, so that would mean I would need some sort of structure that looks like that. Well, how do I get from an alkyne to an alkene? Again, you can use a poison catalyst. So because I don't have a lot of room to write here, I'll do lithium and ammonia. But you could also do Lindlar's catalyst because in this case, being that there's two hydrogens here, there's really no stereochemistry involved that you would need to worry about to give you that product. Okay. And then the last one looks like we're going to have some sort of rearrangement. And in this one, you can do it in two ways, basically. But if you look here on the product compared to the starting material, I have 3 hydrogens and a chlorine. So break that down. We need to do some sort of HCl addition, so a hydrohalogenation. And so if I do one equivalent of HCl, that should get us to the point where we have this. And that would involve a 1,2 hydride shift. Anytime you have a carbocation, you can get a hydride shift. And so in this case, you could do it either from the alkyne to alkene stage or the alkene to alkane stage. It doesn't matter. So that would be one reaction. And then the second one would be hydrogen gas with palladium on carbon using ethanol, or platinum 4 oxide with acetic acid and hydrogen gas. Alternatively, if you wanted to do this with a poison catalyst, so lithium and ammonia or Lindlar's catalyst first, you would get down to this stage. and then you could do the HCl to give the same product. So you have kind of two options there. Either of those options, any of these options, you would get full credit. Instead of HCl, you could have done H2SO4 or H3PO4 or any of the really good acids that are non-halogenated. So you could do that with sodium chloride. We learned that is an alternative method for doing the same sort of chemistry. So hopefully that makes sense. Let me know if you have any questions on that one. And I'm going to pull up the next one. Any questions on what we've done so far? I did bring out my cute teapot for you guys tonight. One of my cute teapots. It's dripping hot tea all down my leg. Ow! Down my leg. I have an obscene collection of cute teapots. That probably doesn't surprise any of you. Okay. So let me... I know, Kenny. Some of you are just here for the ride, aren't you? Okay, so I'm just going to draw the H2SO4 as H+, for simplicity. You're allowed to do thanks, Al. You're allowed to do that if you want, use H+ to indicate strong acid in the system. So I'm going to go ahead and show that getting protonated. Oh, goodness. So you would end up with a carbocation, and technically you would get a 1,2 hydride shift on this. I didn't want to make the mechanism that long for people, so we're just going to give the reaction that would give this product over there. Okay? So the next step is the water is going to come in and attach to that carbocation. So I don't like how I drew that. I'm just making it worse, sorry. The arrow should start on the oxygen. That would give us this protonated stage. Then I need to deprotonate that. You could use either water as your base or the HSO4 minus that you have left over from doing your reaction, which is what makes that a catalyst. Okay. And then the last stage is just to have the enol convert to that keto form. So that picks up a hydrogen, that collapses, and there you go. You can tell, that there's kind of a difference in how I do the reactions from semester to semester, because some of these mechanisms are ones that we did on our last exam, not this one. So if you're looking at that thinking that, it's just because of how I covered things last year. So this is the one where we use a what am I doing? Okay. Where we have an alkene, and we're converting that into an epoxide using a peroxy acid. there were a hot minute of you guys, there were a hot number of you guys that got this wrong on the last exam, so pay careful attention. You may or may not see it again sometime soon. So the first thing that happened, let me remind you that what you get at the end over here is this. And I'm showing that to you very intentionally because this oxygen here is the one that becomes that oxygen there. And this here becomes that there. And this hydrogen becomes that hydrogen there. So I know I color-coded that on the board for you guys once. I'm doing it again now. Because what that leaves us with, if you think about it, is this oxygen here. The one attached to the hydrogen is the one that does the chemistry. Okay, so if you can remember that you get the carboxylic acid when you're done, it makes it pretty obvious which oxygen is going to be the one involved in the chemistry here. Okay, so starting all over again, let's try this. So the nucleophile attacks the electrophile, which would be the oxygen, right? That's going to cause the oxygen-oxygen bond to break and form a double bond between the oxygen and carbon. It's going to pick up hydrogen to form an oxygen-hydrogen bond. And then this last set of electrons will go in and form a bond to that carbon there in the crook of that little arm right there. And that's it. It's concerted, so it happens all in one step, and it's pericyclic, right? So the electrons are flowing in a cyclic fashion. And then I know some of you like it when I number these. Literally every single one of these we've seen so far has the alkene acting as the nucleophile attacking something, so that's always a good place to start. Okay, even if you can't remember anything else, you'll still get 1 point if you show that arrow, I promise. You know, show it going to whatever makes the most sense, and there's a good chance you're going to get a point for it. Okay, so there's that one. My cursor's disappeared from the computer. There we go. When we show the enol, I'm reading. Sorry, Al, I didn't have the text screen up. Walk through the arrows in the second to last step. Are you talking about on this reaction or the last reaction? So answer me on that one. And then Tony said, when we show the enol form going to the keto form, do you want us to use the different arrows, like which one it would prefer? I don't know if I understand. Oh, you're talking about the equilibrium arrows? Yeah, if you want to show that, that's always good to do. A lot of people will just show it as one direction because it so heavily favors that direction. I do tend to try and show it that way to remind people it's in equilibrium. But I think your book probably only shows it like this most of the time. So Al, did I answer your question then with the arrows, or did you need more information on that? Number one. Number four. If you had to put it in words, the words would look something like that. And if you look at this, saying carbocation is a little bit of a misnomer because there is no carbocation because all of this is happening at the same time because it's a concerted reaction. But it would be the one that would be forming a carbocation if this were to happen stepwise. So that's kind of why I state it that way. Okay, and then the last page we have, what type of base would you need specifically to deprotonate a terminal alkyne? I gave you 2 examples. They should be in your notes. On the first day, we covered stuff in chapter 9. So one of them is sodium hydride, NaH, is a very, very strong base. It's much, much stronger than sodium hydroxide. And sodamide, or NaNH2, so NH2 minus, it's like the nitrogen version of hydroxide. It's also a very, very, very strong base. What is an example of an anti-Markovnikov addition? We've legit only learned one, and it was the hydroboration reaction, and that's the only one we're going to learn. So that hasn't changed. What is a tautomer? A tautomer is a variation in structure that swaps or exists in an equilibrium where there's a difference in a proton and a pi bond being placed somewhere. So the one that we looked at were enol and keto tautomers. There are others. Those are the ones that we looked at. But all of them are in equilibrium and all of them differ in a double bond or a pi bond and the placement of a hydrogen. An enol is a specific functional group. Draw an example. I think that one's probably, hopefully, that one's easy for you guys. There's the ene. There's the ol. There is an enol. This would also be an enol. So one would be a terminal enol and one would be an internal enol. And then explain why we see basically anti-addition anytime you have a 3-member ring as an intermediate. So if you remember, we've talked about this one several times. If you have some sort of something here, and it's generally going to have a positive charge on it. And I don't care if it is a halogen, right? We're doing like a halogenation reaction, or it could be mercury, because we're doing an oxymercuration or whatever. Essentially what you have, and I'm going to draw these in big bobbles. So I have a carbon, some rather large group there. And then if this is in the case of hydrogens, there would be a couple hydrogens attached to those carbons. Now I need to add something else big in. Where can it go? It cannot fit in here. There's not enough room. The top atom here is blocking that position. It can only approach from underneath. And it could do so in this case on either one of those because I drew a symmetric make-believe molecule that probably looks like an abstract art project now, but it can only approach from the bottom because it's the only place where something can attack. You're free to make a model of this. You can see it pretty well with a model kit. So the other thing that you can do to kind of help see it is to draw it using perspective drawings. So if I have some carbons and then this is coming out at us, I'm just going to say it's whatever. This is also coming out behind as whatever. We're going to have a bunch of kind of puckering and ring strain. And then on top, I have whatever. Let's do mercury. Okay. So if you think of this in terms of being a tetrahedral group that's kind of bent because of this forced non-109.5 degree bond angle that we're getting basically here. It doesn't like that bond angle. It's making this whole area down here kind of open for attack, whereas anything on top is not going to be able to fit. So A couple of you have emailed me about that one. Hopefully that makes sense. This should roughly look like the picture I drew in class for it, but maybe I drew it in my mind. I don't know, but that's about the best I can do to explain it without breaking out a model kit. Haley asked, for hydroboration, do we have to show the R groups that are attached to boron, or can we just write R? I'm fine with you guys just writing R for the other two groups. Oops, what have I done? So, you know, at some point you'll end up in a hydroboration reaction. You'll have some sort of carbon attached to other stuff. I don't know what it'll be. And that boron would be attached to two more carbons that are identical to that one, because the reaction happens 3 times for every BH3 you add. So you are welcome to put R's there to kind of go through that process. As long as you show one fully, that's fine. So if this was hydrogens here, so like this would be a legit structure you could use during the hydroboration reaction, where those R groups would be ethyl groups because that's what we have over here. And then you'd have, you know, your oxygen attack and have that on here at some point. But I'm fine with you putting R's there. That's pretty conventional to do it that way. Otherwise, you'd have to draw like 18 pages worth of stuff. No one wants to do that. More questions? You guys are kind of quiet tonight. The free radical halogenation reaction? Sure. So I need that bigger. I hope that's big enough for you guys to see okay. Let me know if you need it a little bit bigger. I just have to increase the size. So for a free radical halogenation, what you would be looking for, and I'm being very generic in this reaction. So what you would look for would be some sort of alkane, any alkane, methane, propane, isodecane, a Buckminster fullerene. Like you could, well, that doesn't have any hydrogens on it. So anyway, you have to have hydrogens, but some sort of carbon that has hydrogens on it. I will only show it to you with hydrocarbons. Let's see. So now I've got some chlorines And if you're wanting to see the mechanism, you have to be able to show a hydrogen. So it's one of those things where if you just have the regular skeletal structure, you're going to have to redraw it, but that's often the case, as you've probably noticed. And then, oh, this is hard to show on here. So with the UV light, you're going to get this molecule splitting in half using those weird fishhook arrows. So instead of a full arrow, right, think of it as a half arrow. I am sure whoever came up with that thought they were very, very clever. I'm not entirely sure I agree with them, but whatever. And so that ends up giving you 2 chlorine radicals. So let me show that. I'm just going to show it as I know I have a button for radical somewhere. Here we go. There we go. All right. So you basically need to show at least 1 electron on these, and it can just be the one. You just need to indicate that it's a free radical. So as long as you're showing that one, you should be in good shape. Now with that, you can see if I can pull up a better arrow. I don't like this one. Okay. So now I can show why did that not bring up an arrow? Okay. So I'm going to show that coming in. And if you notice, I'm kind of just showing it going off into space, not really attacking anything specifically. And I'm very intentionally doing that because then the next thing that I need to see is the same sort of thing happening with that hydrogen. There we go. And so that's the bonds that I put there on top are indicating HCl being formed. And then I need to show this bond coming in and forming that free radical on a carbon. So you should end up with something. I really thought for some reason this would be easier to do on here. I was wrong. It's not the first time and it's not the last time, but this was not the easier way to do this. So I have some HCl that was produced, and then I have this carbon radical, and I also have extra leftover radical that we didn't use for anything yet. And so now I just got to make that reaction happen. So I'm going to show the chlorine kind of forming a bond with that one. Oh, come on. There we go. And so with that, that's how you do a free radical reaction. There are 12 hydrogens on this atom, or on this molecule, and that means you could get this done a total of 12 times. I will never ask you to do that. I won't ask you to do it more than once, but that's it. That's how you do it. And again, it's in chapter 6. So if you want to look back in chapter 6, you can peruse, figure out from there. That was rad. I'm really glad. Radical. Ah, it was a radical, actually. I'm glad you recognized it. The drums are about 15 feet from me, so I can't. I need to have Brandon play us like theme music to go along with these videos. Thank you for making me laugh, guys. Other questions? Have a view of my knee. Tony, could you show peroxy acid and cyclohexane with an alkene group on it becoming a cyclohexane and having 2 alcohol groups? That's very specific. I guess I can show that. Are you asking? Well, I actually showed the mechanism for that one in your notes, so I don't know if we need to see that, but any of those are a 2-step process. So if you have some sort of a cyclohexane with an alkene group on it, I don't know if you mean cyclohexene or if you mean cyclohexane that has an alkene coming off of it. It would be the same thing either way. And then if you do the proxy acid treatment with it, which I mentioned we can basically just show it as RCOOOH, which is kind of a shorthand way of showing the peroxy acid in it. Well, Tony, it would be the same exact thing regardless, so I don't think it matters if it's inside or outside the ring. So all you have to do, though, is show the peroxy acid forming. You would get an epoxide. So in this case, the epoxide would look like this. You asked about it being in the ring. It could be also in the ring. I mean, it would just look a little different, but here's an epoxide, right? The chemistry is exactly the same. It's just slightly different placement on the molecule. So I'm not sure why that would matter, but delete that one. Then if we add in some hydrogen, some like HCl or H2SO4, H plus basically, H2SO4, H3PO4, I say HCl, don't do HCl, but sulfuric acid or phosphoric acid treatment with this, which I'm just going to kind of put as H plus. There we go. And then you would need some water in there as well. There we go. So you would end up with a stage where you protonate this, the oxygen on it. There we go. And now that's going to make that oxygen prone to nucleophilic attack. So if you want to show you would expect the oxygen on the water to attack the kind of most inner carbon, just like what we've been doing literally 100% of every time ever on everything else. And we'd have something like that, except we ain't done yet, kids. Because that oxygen would still have a positive charge on it. And we would have to show that getting deprotonated. So what you could use as the base would probably just be more water, or whatever the conjugate bases of whatever acid you used. So hydrogen sulfate, dihydrogen phosphate, if you used phosphoric acid, one of those. Just for making it easy, because this program is a little bit of a challenge to use, as you've probably learned in lab. Oh, I don't like that. I do not like it. It's considered bad form. Well, yeah, Tony, of course. If you're doing it on cyclohexene, you would have cyclohexane 1,2-diol. If you're doing it with this, then it would be off the place wherever you had the alkene. So, but again, the chemistry is the same, so that's all you need to know. The chemistry is the same. There we go. Yeah, you better be making sure. There we go. Finally, at long last, I have answered Tony's question, hopefully. All right. So yeah, wherever you have the alkene, though, you'll end up with the 1,2-diol. In the ring, outside of the ring, without a ring. I mean, it's anywhere where you got the alkene. And, you can form epoxides a couple different ways, so know those. This was one of them. I want us to show the mechanism for adding the X and OH to the alkene. Well, if you've noticed when I show you guys, I mean, you need to know that mechanism because we learned it on the last exam. But when I do a mechanism, I usually keep it a little simpler than that, and I give you a starting material and a product and have you get to there. So all you need to show is the reaction, or the mechanism for the reaction that I show. So you don't have to add in stuff if I've already implied that you've made the epoxide. But I could ask you how to make that epoxide using a halohydrin. No problem. This is always so awkward for me. I don't know why you guys liked this instead of office hours today. But whatever, I'll do whatever you guys are more comfortable with. Oh, let me check my email to make sure nobody's emailed me any questions. Sometimes I get someone who, for whatever reason, is having issues. Well, this is absolutely precious, but somebody sent me an email that is not for me. I'm sorry, but I think you have the wrong email address. They sent like an entire diary from November 17th all the way until April 23rd. The last entry was, you went to the doctor today. You're 19 pounds, 13 ounces, and 28.75 inches long, and Dr. Williams is incredibly impressed with your development. She repeated several times how satisfied she is. So I'm glad that she thinks I'm 19 pounds, 13 ounces, and a little under 29 inches long. That's much larger than I was as a child. So I'm just glad that their doctor's impressed with my development. So it's like a wrong phone call, you know, but wrong email. I get those sometimes, and it's always to my regular Gmail account. So I don't know if there's somebody out there. And it's always family photos from elderly people. So I don't know if there's a Megan Mann somewhere out there that has a very similar email address to me, but it's kind of funny. It's like, and they never respond when I tell them they have the wrong email address. Anyway, completely irrelevant to organic chemistry, but that's what happened when I looked to see if any of you emailed me. I'd like to see all 10 people here try to fit in your office. Yeah, it's happened. It's happened before. The first time I taught biochemistry many years ago, my class, Biochem 2, only had, I think, 7 people in it. And so we had a couple days where, because my office is just across from the biochem lab, and so if we had like a 30-minute incubation or something, we'd go over to my office and sit down and have tea and eat candy. I'm nowhere near cool enough to host a party in my office, but all right. Any more questions? If not, I'm going to get off because I got a lot of work to do tonight, and you have a lot of studying to do tonight. It is a little awkward, isn't it? Them sending me like I've gotten pictures of babies and all kinds of random stuff. My email from this family. You are welcome, Al. I guess I'll say goodbye. I will still have email open, so caveat to email today is that I'm very quickly answering emails. So if you are like, why is she so curt and is she angry at me? I don't know. Some people assume the worst when a professor sends them a curt email, and it's just because I've got a lot to do, and I have about 10 more emails that are probably coming in behind you guys. So if you have any questions, email me, and if I have time for it, I will help you. And if I don't have time for it, I'll tell you where to find it in your book or in your notes or on the internet. So that's what we're going to do tonight. And I will see you guys tomorrow at 11:15. The last thing I'm going to do tonight is grade I have 6 lab reports left from the distillation gas chromatography labs. And so those will be finished tonight. Take about an hour and a half. They take about 15 minutes each. And so I should be able to get that done tonight and get those out to you. So you can start working on that 3rd lab report. And then I think that's probably it. But email me if you have any questions. And then tomorrow after the exam or whenever, somebody maybe email me. I'll charge someone with this. Al, are you still here? We'll tell Al. Al, if you're still here, I need you to email me and remind me to post an answer key for the exam that you take tomorrow, so you'll have it to study for the final. Because I don't think there'll be a way for me to get that back to you guys in that kind of turnaround. It's like 48 hours. So All right. Well, you guys are welcome, and I will talk to y'all later.